Momentum and impulse. You know that an empty shopping trolley is easier to start, stop and steer than a full shopping trolley. Also, the faster it is moving, the harder it is to stop. This property of motion is called momentum. Momentum is mass times velocity, and momentum is given the symbol P, mass m and velocity v, so we get the equation P equals mv. You will have met momentum at GCSE. Momentum is a vector quantity, and so we must state the direction. And if momentum in one direction is taken as positive, momentum in the opposite direction will be taken as negative. A property of momentum you will have met at GCSE is that it is always conserved when no external forces act. For example, in collisions. Here we have a 4 kilogram mass travelling at 3 meters per second towards a 2 kilogram mass. The two will become attached and move off together like this. We can use conservation of linear momentum to find the final velocity v of the two bodies. We know that the momentum before is equal to mass times velocity, which was 4 kilograms times 3 meters per second, which comes to 12 kilogram meters per second. We also know that momentum before must equal momentum after the collision, due to the conservation of momentum. So, the momentum after must equal 12 kilogram meters per second, but that is equal to the mass of the body, which is now 6 kilograms, times their velocity v meters per second, giving an answer of v of 2 meters per second. Momentum is also conserved in explosions. Here we have a cannon containing a cannonball. Both have zero velocity, and therefore the system has zero momentum. When the cannonball is fired, it has momentum in this direction. The cannon is seen to recoil in this direction. If the cannonball has a mass of 10 kilograms and a velocity of 25 meters per second, the cannon a mass of 500 kilograms, and we're asked to find the velocity. You'll notice I've used uppercase letters for the cannon, lowercase letters for the cannonball. We know that the momentum before the explosion was zero, so by conservation of momentum, the momentum after the explosion must also be zero. We can write this as the momentum of the cannon plus the momentum of the cannonball equals 0. Rearranging, we get the velocity of the cannon is equal to minus the momentum of the cannonball divided by the mass of the cannon. Putting the numbers in, we get minus 10 kilograms for the mass of the cannonball times 25 meters per second, the velocity of the cannonball, divided by 500, the mass of the cannon. This gives the velocity of the cannon of minus 0.5 meters per second. The minus sign shows us that the cannon goes in the opposite direction to the cannonball. When an external force does act, momentum can change. Here we have a 200-gram squash ball travelling at 25 meters per second, where it will rebound off the wall at 20 meters per second, and we're asked to calculate the change in momentum. So this is what the ball is doing. The momentum before is equal to 0.2 kilograms, don't forget we must convert into SI units, times 25 meters per second, equaling 5 kilogram meters per second. The momentum after, 0.2 kilograms times minus 20 meters per second, the minus sign showing it's travelling in the opposite direction, giving minus 4 kilogram meters per second. Change in momentum is equal to final momentum minus initial momentum, or minus 4 kilogram meters per second minus 5 kilogram meters per second, giving a change of minus 9 kilogram meters per second. If we'd taken the opposite direction, travelling to the right as positive, this would come out as a change of plus 9 kilogram meters per second. A change in momentum requires a force to act for a given time. The bigger the force, or the longer it acts for, the greater the change in momentum. This property is impulse and is equal to change in momentum and also equal to force times time. We can write this as F delta t, force times change in time, is equal to delta mv. Don't forget we can't separate the deltas here, they just mean change in. This illustrates the importance of following through in ball sports. The longer a force acts, the greater the change in momentum, therefore the greater the speed of the ball. Impulse has the units of Newton seconds, force times time, but as 1 Newton is the force that would give 1 kilogram an acceleration of 1 meter per second squared, can get that from the formula force equals mass times acceleration, we can write Newton seconds as kilogram meters per second squared times seconds, which cancels down to kilogram meters per second, the same units as momentum, as you would expect. Let's look at a problem. A tennis player hits a 200-gram ball approaching at 40 meters per second with an average force of 100 newtons. If the racket is in contact with the ball for 0.2 seconds, calculate the return velocity of the ball. Well, the momentum of the approaching ball is equal to mass times velocity, 0.2 kilograms times 40 meters per second, giving it a momentum of 8 kilogram meters per second in one direction. Impulse is force times time, which is minus 100 newtons, the force will be in the opposite direction to the motion of the ball, times 0.2 seconds, giving an impulse of minus 20 newton seconds. But impulse is equal to change in momentum. Final momentum will be equal to initial momentum plus the change in momentum, which in this case is 8 kilogram meters per second, plus minus 20 kilogram meters per second. Notice I've gone from the impulse units of Newton seconds to the momentum units of kilogram meters per second here, giving a final momentum of minus 12 kilogram meters per second. Final velocity is equal to momentum over mass, which is minus 12 kilogram meters per second over 0.2 kilograms, or minus 60 meters per second. This is 60 meters per second in the opposite direction to the initial velocity, which we took as positive. The longer the contact time, the greater the change in momentum, and so the greater the velocity of the ball, hence the importance of following through. Looking at another aspect of impulse, cars are designed with crumple zones and airbags to increase the time taken to reduce the occupant's momentum to zero in the event of a crash. The longer the time taken, the lower the force is exerted, so reducing the risk of injury to the occupants. The car on the left has no crumple zone, and so stops instantly on impact with the wall. The car on the right has a crumple zone, and so takes slightly longer to come to a rest. The longer it takes, the lower the force on the occupants, and so the lower the risk of injury. If the crumple zone means the car comes to a stop over 0.5 seconds instead of 0.1 seconds, the forces on the occupants will be 5 times lower. In terms of energy, the kinetic energy of the car has been absorbed as the car deformed, producing heat and sound. This reduces the amount of energy going into the occupants of the car in the form of injuries. This idea of increasing the time to come to a stop and so reducing the force is used in many areas, including in airbags and seatbelts to reduce injuries to car occupants, in crash mats to reduce the impact on athletes and gymnasts, and in running shoes to reduce the impact on joints caused by repeated impacts with the ground. In each of these, kinetic energy has been transformed into elastic energy as well as thermal energy. Here we have a high jumper at the top of their jump. At the moment they have gravitational potential energy. They fall towards the crash mat, and at this point, if the crash mat was solid, they will be brought to a halt very suddenly, involving huge forces and certain injury. However, at the moment of impact, the jumper has kinetic energy. They also have some gravitational potential energy, as they still have some distance to fall. The crash mat deforms, and the energy of the jumper becomes elastic energy plus thermal energy of the crash mat. This is covered in more detail in the video on energy changes.